Welcome to Mindcast, the podcast where we dive deep into the fascinating intersection of technology, science, and human understanding. I'm your host, Will, and today we're tackling a topic that's been buzzing through the scientific community and beyond. The AI physicist paradox, why AI can't replace human scientists yet. Now, you've probably heard the hype. AI is going to revolutionize everything, solve climate change, cure diseases, maybe even discover the next theory of relativity. But here's the thing. When we actually put these systems to the test in real scientific scenarios, something fascinating and humbling happens. They fail, spectacularly. Today, we're going to explore why that is, starting with an eye-opening experiment by physicist Sabine Hossenfelder that perfectly illustrates the gap between AI expectations and reality.
So let's start with Dr. Sabine Hossenfelder. And if you don't know her, you should. She's a theoretical physicist who's become something of a science bullshit meter on YouTube. Her motto is, as simple as possible, but not any simpler, and she's dedicated to cutting through hype and getting to the truth. Recently, she conducted what I think is one of the most revealing experiments about AI's current limitations. She took some of the most advanced large language models available. We're talking GPT-5, Gemini DeepThink, Grok 4, Claude Opus 4.1, basically the cream of the crop. And she gave him a simple task: generate a novel physics idea. Not summarize existing knowledge, not answer a textbook question, but come up with something genuinely new. The result? Complete and utter failure. Every single one of these supposedly advanced AI systems produced what she brilliantly termed vibe physics. Text that sounds like it could be physics, uses all the right jargon, adopts an academic tone, but is completely devoid of actual scientific substance. Now, here's the fascinating part. These weren't just any AI systems. These were the models that can write poetry, solve complex coding problems, and engage in sophisticated conversations. Yet when asked to do what human physicists do every day, think creatively about the fundamental nature of reality, they produced nothing but sophisticated-sounding gibberish. So why did these incredibly sophisticated systems fail so dramatically? To understand that, we need to peek under the hood and see how these large language models actually work. And I promise it's not as mysterious as the marketing makes it sound. At their core, LLMs are based on something called the transformer architecture, basically a really clever way of processing sequences of words. The key innovation is something called self-attention, which allows the model to figure out which words in a sentence are most important to each other. But here's the crucial part. These systems are trained to do exactly one thing: predict the next most statistically probable word in a sequence. That's it. They're shown trillions of words from the internet, and they learn the patterns of how words typically follow each other. Think of it like this. If I give you the phrase, "the cat sat on the," you can probably predict "mat" comes next. Not because you understand cats or furniture, but because you've seen that pattern before. LLMs do the same thing, just on a massive, incredibly sophisticated scale. The training happens in two phases. First, they learn these statistical patterns from huge amounts of text. Then, they get fine-tuned using human feedback to make them more helpful and conversational. But fundamentally, they remain statistical text predictors. And here's why this matters for science. True scientific breakthroughs are, by definition, low-probability events. They're radical departures from existing knowledge. But a system optimized to predict the most likely continuation based on past text is fundamentally conservative. It's designed to reproduce the statistical average of what it's seen before, not to venture into genuinely new territory.
Now, let's dig into why LLMs fundamentally can't do real science. At least not yet. There are several critical limitations that go to the heart of what science actually is. First, there's the mathematical problem. Real physics isn't just words. It's mathematics. A genuine physics theory consists of equations that make precise, quantitative predictions. But LLMs work with words, not mathematical relationships. They might mention space-time curvature or quantum fields, but they can't formulate the differential equations that actually describe these phenomena. Second, and this is huge, they can't distinguish between correlation and causation. Through training, LLMs become incredible at learning that certain concepts appear together in text. They know gravity is statistically associated with mass and curvature, but they have no understanding of why this is the case. They lack a causal model of how the world actually works. Scientific theories, in contrast, are fundamentally causal explanations. They don't just describe what happens, they explain why it happens in a way that allows for novel predictions about things we haven't seen yet. Third, there's what I call the falsifiability problem. The cornerstone of science is that theories must make predictions that can be proven wrong by experiment. But the vague, conceptually muddled outputs that LLMs produce are often so ambiguous they can't be meaningfully tested against reality. And finally, there's the empirical disconnect. LLMs are text-only systems locked in a world of words. They can't observe phenomena, design experiments, collect data, or verify their outputs against the physical world. They're powerful tools for manipulating language. But science is ultimately about understanding reality, not just talking about it.
So, if the limitations are this clear, why do we have such inflated expectations about AI's scientific capabilities? The answer lies in what I call the narrative machine, a powerful combination of science fiction, marketing hype, and media sensationalism that shapes our perceptions. For generations, our primary interface with AI has been through movies and TV shows. From HAL 9000 to Commander Data, popular culture has portrayed AI as human-like intelligence that thinks, reasons, and creates like we do. This creates a powerful cultural backdrop that primes us to see any advance in AI as a step toward this fictional endpoint. When an LLM generates fluent, coherent text, it's natural for us to attribute human-like understanding to it. After all, in our experience with other humans, linguistic fluency is a reliable indicator of intelligence. But as we've seen, LLMs achieve fluency through statistical pattern matching, not understanding. Then you have the marketing machine. Technology companies have clear incentives to present their systems in the most transformative terms possible. Instead of transformer-based statistical language model, we get descriptions of AI co-scientists and virtual collaborators that can accelerate scientific breakthroughs. The language deliberately blurs the line between a tool that processes data and an intellectual partner capable of creative thought. The media amplifies these messages because, let's face it, AI discovers theory of everything makes a much better headline than AI helps process data more efficiently. This creates a feedback loop where hype drives investment, which drives more hype, potentially diverting resources for more fundamental research. Now, before you think I'm completely down on AI and science, let me be clear. AI is already transformative in physics and other sciences, just not in the way the hype suggests. The reality is that AI has been an indispensable tool in physics for decades, but its role has been that of a highly specialized, powerful instrument, not a creative theorist. At the Large Hadron Collider, machine learning algorithms sift through petabytes of data to find the faint statistical signatures of new particles. In cosmology, AI runs vast simulations of the universe's evolution to test different theories about dark matter and dark energy. In astronomy, AI classifies millions of images from sky surveys. In all these applications, AI isn't generating new physical laws. It's applying its pattern recognition capabilities within the framework of existing human-created theories. It's a tool for accelerating computation and analysis, not a substitute for conceptual insight. This is the real future of AI and science, not as replacement scientists, but as incredibly powerful co-pilots that augment human intelligence. They can synthesize vast amounts of literature, help with complex coding tasks, and even serve as tireless brainstorming partners, generating numerous combinations of ideas that might occasionally spark genuine insight in human researchers. The key is the human in the loop, the scientist who provides the critical reasoning, oversight, and connection to empirical reality that turns statistical text generation into actual scientific progress. So, where does this leave us? The AI physicist paradox reveals something profound about both artificial and human intelligence. Current AI systems, no matter how sophisticated, are fundamentally different from human cognition. They excel at pattern recognition and language generation, but they lack the causal reasoning, mathematical insight, and empirical grounding that define scientific thinking. But here's what I find most fascinating. By understanding these limitations, we can actually use AI more effectively. Instead of expecting it to be a creative genius, we can leverage its strengths as a research accelerator while maintaining human oversight for the critical thinking components. The future of AI and science isn't about replacement, it's about augmentation. It's about creating powerful collaborations between human creativity and machine computation, where each contributes what it does best. As we continue to develop these technologies, we need more nuanced conversations about their capabilities and limitations. We need to move beyond the hype cycle and develop genuine AI literacy that recognizes both the profound power and the fundamental constraints of these systems. Thanks for joining me on Mindcast today. Until next time, keep questioning, keep thinking, and remember, in the quest to understand our universe, human insight remains irreplaceable, even as our tools become more sophisticated. I'm Will, and this has been Mindcast.